Let's look at a few examples with relativistic dynamics. So consider example 12.11, where we have a charged particle in a circular motion in a magnetic field. So let's say that this is our magnetic field B, and this charged particle is moving around in a circular path with a velocity u. It has a charge of q, and the radius of the path is r. Now, the force you would feel, the magnitude of the force, would be the charge times the velocity times the magnetic field. And since I've drawn it such that the velocity and the magnetic field are perpendicular, I don't have to worry about the cross product right now. If I now look down on this from above, what I would see is this charged particle, which is moving with some momentum p, and then after going through an angle theta, or sorry, d theta, after going through an angle d theta, it now has a momentum p plus dp. So in the end, dp is the momentum p times the angle d theta, which is basically just the arc length formula. Okay, so if we want to look at the force as the change in momentum of the change in time, ordinary time, then we would have the momentum and the change in angle with respect to time, which is essentially the momentum times the speed divided by r. So I skipped the step where the angular velocity is equal to the speed divided by r. Okay, so our force is the momentum times the velocity divided by r. And so now if you think about it non-relativistically, then the momentum is mass times velocity. So the force is the mass times the velocity squared over r, which is the mass times the centripetal acceleration, like so. Now, if we wanted to treat this relativistically, then the momentum is equal to gamma times the mass times u. So if I think about it, if I treat the velocity relativistically and the momentum relativistically, then this equation, F is equal to momentum times velocity divided by r, is relativistically good. And so in the end, I could write my, I could set this equal to QUB, and the U's cancel, and so the momentum is equal to Q times B times R. So this equation here is valid both relativistically and non-relativistically, because we haven't said anything about Q, B, or R in terms of their conversions in special relativity. So this equation works whether you choose to measure your momentum relativistically or non-relativistically. An interesting thing to consider is that if we have a collection of particles, right, in non-relativistic mechanics, what we often do for a system like that is come up with a center of mass where we take the mass of every individual particle and sum it according to its position with respect to some origin that we're measuring. So this is M1, M2, Mi. So you just sum them up like that. And in that case, the momentum of the entire system is just the mass times the velocity of the center of mass. Okay. Now, if we want to think about this in terms of special relativity, the mass may not be a good choice because we said in earlier lectures that the mass can, if you wanted to take a look at this equation, I could apply the gamma to the mass, or I can apply the gamma to the velocity. So mass is going to change with the relative speed of other frames of reference. So instead, a better quantity would be the center of energy, where we can treat the energy now relativistically. So the center of energy, and the fact that energy incorporates both momentum and mass, so kinetic energy and rest mass. So I could write this as 1 over the energy of particle 1 times its position, and then the total mass is the energy divided by c squared. So that's the total mass of the system. And therefore, the total momentum of the system is E over c squared times the velocity of the center of energy of the system. Okay, so that was just kind of an aside. What we could do now is take a look at another problem, and that is if we wanted to look at example 12.13, and so here we have a coil which has positive charges moving around it, like so. It has a magnetic dipole moment, and it has an electric field which has been applied in one direction. And so what's going to happen is these charges are going to move. So I could say this is the speed of the charges at the top, this is the speed of the charges at the bottom. It has a width to this coil, and it has a length to the coil, like so. And so we want to find what is the total momentum of all the charges. Okay, so now I'm not going to consider the left and the right of the coil, because in that case the momentum is going to cancel each other. I'm only going to consider the momentum at the top and the bottom of the coil. And so what we have is the number of charges plus basically the number of charges oh, I'm sorry. The momentum going left and right cancels, not momentum up and down. The momentum left and right cancels. And so if we consider now the momentum of the number of charges that are moving to the right, and n minus is the number of charges moving left. And so just to clarify, since the electric field is pointing up and down, is pointing up, it is not going to be, say, pushing a force in the direction of motion. So it's not going to speed up the charges in the top and the bottom. And so, okay, so we'll come to that in a second. The current, in this case, is the charge density times the velocity. And what we want to see is, well, do we get a steady current through the whole thing? We should, or else, or if we don't get a steady current, the charges are going to start to pile up and collide. So therefore, the current you would get is the charge of each particle, the number of the particles moving in the top part of the coil, divided by the length to get the charge density, times the speed in the top coil. And that should be the same as what goes on in the bottom, because we should get steady currents flowing in this coil. Okay. Okay, so then if we now consider, so we could rewrite this as the number of charges, either plus or minus, times their speeds, either plus or minus, is equal to the current times the length divided by the charge. So all those things are constant in the problem. So if we look at this non-relativistically, the momentum is the mass of the particle times its speed. So that I'm going to call this one particle. So the total momentum is the mass of each particle, the number of the charges plus the number, so basically the ones moving the top, minus the number moving in the bottom. And so what I get is factor out the m, and I get ILQ minus ILQ is equal to 0. So we expect. We have a steady current flowing through this coil. If we now look at this relativistically, then the momentum of one particle is gamma times its mass times its speed. Again, this is just one particle. And so the total is gamma plus mn plus u plus minus gamma minus mn minus u minus. And so what you notice is you have a different gamma factor because it depends on the direction of the velocity. Because gamma, if you remember, is 1 over 1 minus, well, it depends basically on the, it depends on the direction of the velocity. In one case, the relative velocity is moving left. In the other case, the relative velocity is moving to the right. And so what you get in the end is, factor out an m. I can factor out the ILQ, which is essentially the n plus u plus n minus u minus. But I get gamma plus minus gamma minus. And that is not equal to 0. And so what you get is you get not a zeroing of the momentum, but you get a non-zero total momentum to the system. And that's because, depending on your point of view, the charges are either moving to the left or they're moving to the right. So there is some kind of contraction, let's say, that's going on. Now, if we look at the work that's being done, the work is equal to the force times the length. So the QE, and now the length is, okay, the charge, the force is QE, and this is the length W. So that's the amount of work being done, moving the charges, either pushing them up or slowing them down as they come down. If I now look at this, gamma plus minus gamma minus is equal to QE, the width, divided by MC squared. And so in the end, what I get is a momentum, which is the current times the length times the vector field times the width divided by c squared. The dipole moment is IL, the width, basically the area times the current. So therefore the momentum is 1 over c squared, the magnetic dipole moment crossed into the electric field.